Right, last one in this session. Modern artificial intelligence, big data, analytics, big data and analytics applications in Satcom monitoring and control. And this is by Hakan Savaşan from Profen.
Thank you very much for announcing my name. Very neat, very. Hello everyone, I am Hakan Savaşan of Profen. I'm going to talk about modern artificial intelligence, big data and analytics applications in Satcom monitoring and control. In fact, it's a definitely pure software issue. You know, for the last 10 years almost, artificial intelligence, big data and analytics is in our world. So here I'm going to propose a system which will ease our CAPEX and OPEX in Satcom monitoring and control. Let's start with why we need Satcom monitoring and control. Usually they are software-intensive solutions that is being used for the large ground systems. These are very big systems that we have to invent a lot of money. So these systems, in these systems, we must ensure continuous operation of the strategic system, minimize operator errors, downtime due to operator errors, minimize downtime due to other failures. On the other hand, minimize maintenance and repair costs and maximize reliability and sustainability of the system. So here we're going to use Satcom monitoring and control systems. They are usually real-time monitoring and control systems, but by using the cutting-edge artificial intelligence technology, we can provide AI and machine learning-powered cloud-based predictive maintenance system. So let's go with the what is predictive maintenance. Let's start with the basic definition. Let's say that the reactive, we start with the reactive maintenance. Reactive maintenance is the, if it ain't broke, don't fix the system. This is the very old-fashioned way of handling these large systems. If machine fails, then you fix it, but you may encounter problems like that. There is a preventive maintenance afterwards. This is based on manufacturer's schedules, time or observations, and this is a scheduled maintenance. Whatever the condition of the equipment is, you start maintenance. You have maintenance cards and a scheduled table. Weekly, monthly, or quarterly, you make some maintenance on the system. Condition-based maintenance systems are the most used ones nowadays for the large ground systems. This is based on monitoring and control of the system with software. These are real-time, just like real-time command and control systems that is sensing the telemetry data streaming from the system, all equipments of the system, and then putting some algorithms inside the software and trying to detect the anomalies or error conditions in real time and show or warn the operators in real time. But this will not tell us what will be going on in near future at the system. We can just see the existing position of the system. Predictive maintenance comes to life with the Industry 4.0, and it's based on usage and wear characteristics to predict the failure of the system. In fact, here we are trying to predict the near future or mid future and how will system behave in the near future, and if there will be any kind of equipment failure, and if we can do anything about that failure. This is the definition of predictive maintenance. It's for almost 15 to 20 years it's at the market and being used by the market. So this is an example showing the difference between predictive maintenance versus scheduled maintenance. Scheduled maintenance is in the previous, I can go, it's, this is here, I told about that, it's preventive maintenance. So here we schedule the maintenance quarterly, weekly, or monthly, and then whatever the status of the system, we apply the maintenance. Maybe we change some parts of the system, so this is costly, time-consuming, and maybe if there is any kind of equipment you can still continue using, you cannot use it if you change it. But for the predictive maintenance, you sense the all incoming data, which is called telemetry data, and you're going to maintain the system at the optimal moment, because the system will tell you that, say, in 3 years, in 3 days, your bug will go out of functioning. So at that time, you can change the bug or do any kind of maintenance. This is the optimal maintenance scheme for the systems. Before going on, related with how we can apply the artificial intelligence and machine learning, let's go through this is the usual path, how we can go from data to intelligence. First, we have the data. We are talking about big data. Nowadays, big data means we have 3 V's at big data: volume, veracity, and velocity. It's a huge amount of data coming in a speedy way, and it is not a structured data. For many years, we are related with the structured query language and relational databases, but nowadays the data is not structured. It's non-structured, so you have to store it in a NoSQL database. If you process the data, it will be information, just pure information for some statistical processing methods and any other things. If you process the data, it will be information. But with the cognition, with the understanding of the data, now you will have the knowledge. Knowledge means now you know what is going on, just what is going on, not the other things. If you do pattern extraction from your knowledge, now you start understanding both what is going on and how it had happened. And after inference means making some decisions related with the data, which means that related with the information. Now you know why it did happen. Maybe everybody is familiar with the 5 whys. This why is very important to understand the root cause of the problems. This is the typical way from data to intelligence. So we need to use the same scheme for predictive maintenance. This is a typical technical infrastructure for predictive maintenance system. On the left-hand side, you see the sensor layer. Sensor layer is very important. You have to put adequate sensors for the all subcomponents or equipment of the system, and what we call is the telemetry data. There should be a telemetry data incoming from the connection layer to cloud infrastructure. Connection layer is very important. Remember the discussion about the edge computing of the 5G. This is something like that. Nowadays we can put a lot of processing power in very small devices. So in connection layer we can process some kind of data, which means that we can provide data persistency, security, and unification of the interfaces, legacy interfaces to the middleware, to the cloud infrastructure. Middleware is an important piece of software here related with the publisher and subscriber mechanism. There are producers of the data and consumers of the data, and middlewares, in modern middlewares, this could be handled automatically by the software. Of course, in the cloud infrastructure, you need a huge distributed database. This is the cloud infrastructure. This could be at premise, managed services, etc., Amazon Web Services. There are a lot of cloud infrastructure that you can buy or install at your site. In that the cloud infrastructure, with the streaming data or offline data, you will have models that you will use, both models and data you will use for your machine to learn the main patterns of failures, and then afterwards when you train your models, your computer will start learning by itself. This is what we call machine learning, and it will do data analysis for you in the cloud infrastructure. Of course, you will need a presentation layer, both for the operators or the decision makers, and you will have predictive maintenance suggestions for maintenance workers, and for the operators you will have the other presentations, other dashboards related with the system. This is a typical infrastructure. This is a Pareto chart showing the results of Profen's, this is compiled from the Profen's ticketing system. You know, we have an after support team, and this shows us that this is a real, this is based on the real data. You know, on the left-hand side, you see the percentages of the root causes. There are 5 root causes here. RX and TX losses. This is related with the frequent causes of failures of antenna systems. If it happens in your antenna system, then it will start functioning. Motion system failures, failures due to external forces, antenna gain losses, and transmission line losses. When you hit one of them, your antenna stops working, doing its main function. So if you look at it, on the right-hand side, you see the cumulative percentages. I think everyone is familiar with the Pareto chart and how to read the Pareto chart. So here, 2 main causes, RX and TX losses and motion system failures, represents almost 66 to 65% of the losses, which means that we can easily track these root causes by using a predictive maintenance system and prevent system being stopped functioning. These are other examples of failure conditions that we cannot catch, and then system stops functioning, and then when we go to the field, we observe that, okay, there are these kind of problems, and systems stop functioning. This is the value proposition of AI-based predictive maintenance. It's order of magnitude. Yes, of course, you have to make some CapEx before installing the system, but for the lost production time, the purple ones are the responsive maintenance, the results of the responsive maintenance. It's about $3,500 US dollars, the cost of the lost production time, lost employee time, and the lost for repair. This is an example showing the value proposition for the artificial intelligence-based predictive maintenance systems. Thank you very much for listening to me.